Inside silicon, the technology behind everything. Powered by Semionix.
We live in a world that feels impossibly fast, right? AI models get smarter in just a few months, and our apps seem to update every other week. But there's this really strange paradox at the heart of it all. The actual physical hardware that powers this entire revolution, the computer chip, takes years to create. So, let's dig into why the very foundation of our super-fast world moves, well, so deliberately slow. I mean, just look at this contrast. Over here, you've got software and AI iterating at a breakneck pace. And over here, this silicon chip. It's operating on a 5-year timeline. Now, this isn't because the engineers are lazy or the companies are clumsy. It's because silicon has to play by a set of rules that software gets to completely ignore.
So, that's the big question we're tackling. What's with the massive gap? Why can't we just, throw more people at the problem and speed up chip development, like we do with everything else? To get the answer, we have to go on the journey ourselves, from a simple idea all the way to a finished piece of silicon.
And this, right here, is the most important thing to get your head around. A chip isn't just a blueprint or some elegant code. It's a real, physical object. And it's engineered at a scale that is just mind-bendingly small. We are literally talking about arranging atoms. And that simple fact is where our 5-year journey really begins.
You see, for the first 2 years of its life, a brand new chip doesn't even exist in the physical world. Not at all. It's basically a ghost in the machine, a purely digital idea that's being carefully built and tested long before a single atom ever gets moved.
So year one is all about high-level architecture. What does this chip need to do? How much power can it use? Can we even physically make this thing? Then in year two, that big plan gets translated into a super detailed blueprint called RTL, which is basically the source code for the hardware. And from there, the really grueling part begins: verification.
And just look at the scale we're dealing with. This isn't a few hundred or a few thousand parts. A modern high-end chip has tens of billions of transistors, and every single one of them has to be perfectly placed and connected in this digital model, and they all have to work flawlessly together.
And this is exactly why that perfection is so critical. If there's a bug in your favorite app, no big deal. The company just pushes out a software update and it's fixed. But you can't do that with hardware. You can't patch silicon. Once that chip is made, the design is literally set in stone. A mistake is forever.
This right here explains why the design phase is so incredibly slow. The cost of getting it wrong is just astronomical. Teams will spend more than half their time just trying to break their own design, running millions of simulations to hunt down one tiny little bug. Because if they miss it, it could turn a billion-dollar project into a pile of very expensive sand.
All right, so after 2 years stuck in the digital world, our chip is finally ready to face reality. And this is where the rules of the game just completely flip. We're leaving that clean, predictable world of logic, and we're entering the messy, unforgiving world of physics.
I absolutely love this phrase because it is so true. All those perfect digital models and flawless simulations, well, now they have to actually work with real electrons, real atoms, and real materials. And let me tell you, physics does not care about your project deadline. Year 3 is all about physical design. This is where that digital blueprint gets translated into an actual physical layout, literally figuring out where to put billions of transistors and how to run the microscopic wires between them. Then, in year 4, the factory, or fab, starts developing the incredibly precise manufacturing process to actually build this one specific design.
So what is a fab anyway? Well, it's not just a factory. It's one of the most advanced, most controlled environments on the entire planet. It's a place where we manipulate the laws of physics at a scale that's almost unbelievable, all to turn sand into intelligence.
Get a load of these conditions. The temperature inside is more stable than in a high-tech science lab. The air is literally cleaner than in a hospital operating room. And the vibrations? They're controlled down to the atomic level. Why all the fuss?
because a single speck of dust or the tiniest little tremor could wreck an entire batch of chips.
And to get that kind of control, you need some seriously incredible machines. This is the price tag for just one of them, an extreme ultraviolet or EUV lithography machine. These things are used to etch the impossibly small patterns onto the silicon wafer, and they are, without a doubt, some of the most complex machines humanity has ever built.
And that really gets to the heart of this physical battle. Making a chip isn't just an assembly line process. It's more like an act of experimental physics that you have to repeat millions of times, perfectly. You're basically coaxing atoms into forming structures that can think, and that is a profoundly difficult thing to do.
Okay, so 4 years of design and development are down, the chip is finally being made, but we are not done yet, not even close. Welcome to the final year, which, as any engineer will tell you, is almost always the hardest part. Getting it to work reliably and at a massive scale. So this final year boils down to two main things: yield optimization and packaging. Packaging is pretty straightforward. It's just putting the delicate silicon die into its protective case. But yield is where all the time goes.
So what is yield? Well, simply put, it's the percentage of chips on a big silicon wafer that actually work the way they're supposed to. When you're building things at an atomic scale, some of them just aren't going to be perfect. And getting that percentage of good chips up is this slow, painstaking process of tiny little tweaks and tons of statistical analysis.
This chart shows the struggle perfectly. An early manufacturing run might only have a yield of, say, 60%. But to actually sell the thing, you need to be up at 90% or higher. And that journey, from 60 to 90, can take a full year of relentless microscopic refinement. It's the difference between having a cool science project and having a real product.
And this really brings us to the fundamental truth that separates hardware from software. You can't just throw more engineers at the problem and expect physics to speed up. Atoms have their own speed limit. You can't, file a bug report against quantum mechanics. This slow, deliberate process is just baked into the cake.
Okay, so we've walked through the entire 5-year journey. Now we can finally answer that first question we had. What's the real bottleneck holding back the speed of hardware innovation? Turns out it's not just one thing.
The answer is really a combination of these three gigantic forces. First, you've got physics, which sets the absolute, non-negotiable rules of the game. Second, you have money, which dictates who can even afford to build these multi-billion-dollar fabs. And third, you have geopolitics, because no single country has everything it needs. Building one chip requires a ridiculously complex global supply chain.
And that brings us full circle, right back to our paradox. The reason AI and software can move so lightning fast is because they get to stand on the shoulders of this incredibly slow, deliberate, and reliable silicon platform. Software's amazing speed is a direct result of hardware's patient, 5-year march against the laws of physics. So, the next time you see a headline about some amazing new AI or a game-changing app, just remember the invisible journey behind it. Every single one of those breakthroughs is powered by a chip that started its life 5 years ago. And that leaves us with a pretty cool final thought. What incredible things are being made possible right now by this painstaking atomic-level engineering that we won't even get to see for another 5 years?
Inside silicon, the technology behind everything. Powered by Semionics.